Begin. All right. Hello. Today, a totally new topic. What's the most exciting mathematical subject that you can possibly think of? You guessed it. Polynomials.
There you are.
Good. All right. First, an introduction. Take a function. Here it is. 2x cubed minus 5x squared plus 3x minus 4. Alright, that's a pretty simple function. I would like you to compute f of 6. Go. No waiting.
I'm freaking out.
Nope. Evidence at this table suggests that this is annoying because people are getting different answers. Yeah, these numbers are like big and stuff, and like it's kind of a drag. Even though they're all integers, it's like 2 times. You guys just know what 6 cubed is offhand?
216.
It's like 216, and then it's like 36, and then like 3 times 6 minus 4. I have to do like more math. Like 432 minus, oh boy, 115 minus like 180 plus 18 minus 4. Okay, now like professionals will like add the positive numbers together to get like 450. Am I even doing this right? Yeah, 450 and then like minus 184. That may or may not be the best way to do this. So I guess that's like something. What is that?
66.
Yeah, 34 less than 300. 266. Okay, good. So that was like fun. Alright, I got something else for you. Watch this. It's gonna blow your mind a little bit. Take this same function, 2x cubed minus 5x squared plus 3x minus 4, and perform the following strange algebraic manipulation on this function. Alright, first, take the first 3 terms and notice that they all have an x. So factor that x out. Yeah. Okay. Leaving us with 2x squared minus 5x plus 3, and then minus 4. So it's not true factoring because you still have like 2 terms, but it's like something. Okay, good. Now, cool. Okay, now notice that within this like quadratic, like these 2 numbers, these 2 terms also have an x. So like take an x out of that. All right. So then that's like 2x minus 5. And then like plus 3 minus 4. All right, and probably just like that's good enough. Alright, so now, suddenly, in this new world, we can compute f of 6, like, very, very easily, like, in our heads even. Watch this. Take 6. Plug it in. Just, like, put your pencil down. Everyone just do this kind of in your head, right? 2 times 6 is? 12 minus 5. 7 times
42.
6 is 42, and 3 is 45 times 6.
No idea.
No, you do. It's like,
It's just 266.
Yeah, it's like 270, right? Because it's like 6 times 45 is like, yeah.
It's just 266.
Boom.
Because you have the
Whoa!
answer.
Suddenly that. Sujay, what's up?
It's a function nested linear function.
Yeah, that's exactly what it is. Okay, so let's scrutinize this process a little further, shall we? What is really happening here? Yeah, good. The right answer. Okay, so let's scrutinize this process a little bit. What are we really doing, I guess? Well, we're starting with, the first thing we start with is this first number, 2. So it's kind of like, sort of like the algorithm, so to speak. The algorithm seems to be, first start with a 2. And then, I'm going to sort of put commas here to indicate like the order in which we do things. First start with 2. Then multiply by the input, which is x. Then subtract 5. Then multiply by x again, and then add 3, and then multiply by x again, and finally subtract 4. Okay, so rephrased in this way, suddenly we can kind of sort of see like a pattern going on here. Well, this strange method of sort of factoring is really like yielding some algorithm of computing any particular input to this function by taking these numbers, which after all, like what are these numbers? Like 2, -5, 3, and -4. They're just like the coefficients. So apparently what I've just showed is that if you want to compute f of some number, x, then you just take the first coefficient of the polynomial, multiply by that input, then add the next coefficient of the polynomial, multiply by that input, add the next coefficient of the polynomial, multiply by that input, add the next coefficient, so you're done. Right? This has a name. This thing is called synthetic substitution. And there is a cute little algorithm for this, which says, all right, take 2, -5, 3, -4, and then you sort of write the numbers along the top, the coefficients of the polynomial, and then like over here, this is at least the way I do it, I put in a little box the number that I'm plugging into this function. And now, for purposes of sort of keeping track of what's going on, we just sort of like write the answer over here. So it's like, okay, watch this. First we start with a 2, so I put a 2 here. Then the next thing I'm supposed to do is multiply by that x, right? So I do 6 times 2 is 12, and I put the little 12 here. I put it there so that I can immediately do the next step, which is to add it to the next coefficient. So now I just add that column, and I get a 7. I take that result, I multiply it by the input again. You guys following this?
Yeah.
42. Add the next coefficient, multiply by the input, and then add the
That's tough.
last one too. Just done. Yep. Cool. All right. So good. All right. Now that was like a thing. Put that kind of off to the side. And what I really want to talk about, well, what I want to talk about for a minute is polynomial long division. Oh yeah. Polynomial long division, the most exciting part of mathematics. Let's review. You learned this last year. So I'll just give you a problem.
You're not in the
6x cubed minus 13 squared minus 6x equals 12 over 2x minus 1. Go. You guys all remember how to do this? That is 2. All right. Look up when you're done. Alright, so it's like you go, alright, how many times is 2x going to 6x cubed? Answer 3x squared times, here, I'll do color. So this is 3x squared, and then you like multiply back through, you get 6x cubed minus 3x squared. Now, what makes polynomial language kind of hard is you have to like keep track of all these negatives. I think I'm doing this right. So negative 13 minus negative 3 is like negative 10. Yeah. And then bring down the negative 19. Okay, how many times is 2x going to negative 10x? Answer, sorry, negative 10x squared, negative 5x times. So then you multiply back through, negative 10x squared plus 5x. Then you subtract, so that's like negative 24x, right? Because like, yeah. And then plus 12, and then that goes in negative 12 times. And so that is just negative 24x plus 12. And so, okay, in this case it went in evenly, yeah? Everyone got this under control? Alright, so I am prepared, therefore, to say that the answer is that when you divide this cubic by this linear function, then you just get the quadratic expression 3x squared minus 5x minus 12. And you can check that this works by just multiplying these two together, and you should get that. Alright, cool? Cool. Okay, let's do another one. So here we go. 6x. Alright, this time I got that it did not go in evenly. Is this what you got also?
Yeah.
Yeah, so if you're careful and you don't make any subtraction or algebra mistakes, then math happens and it's like boom, 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 and we end up here with like this 46. And so what is this? Okay, so the algorithm just terminates at this point. So what is the significance of this? What happens when I divide this cubic by x minus 2? We have a remainder, but yeah, but before we get to the remainder, like what is like the answer, so to speak?
It's like 6x squared plus 9x
minus
2 plus 46
46, and then the remainder.
46 over x minus 2.
Okay, good. All right. So yeah, this is sort of the general idea. All right. So okay, cool. If everyone is comfortable with this, then it means you like get the general gist of polynomial division. Okay, but before we so then that's kind of more or less all you did with this last year, I think, basically. But this unit that we're working on now is sort of polynomials. So I'm going to rephrase what's happening in this box as a statement about polynomials by multiplying through by x minus 2. So if I multiply through by x minus 2, I get a slightly different statement that says 6x cubed minus 3x squared plus 4x plus 2 is, well, it's this quadratic, 6x squared plus 9x plus 22 times x minus 2, and then just like plus 46. Cool. Okay, so this is to be seen as like really the exact same statement, kind of just in a slightly different form. And in fact, this is maybe even more clear, right? If you multiply these out and you add 46, you're just going to get exactly this cubic. All right, but writing it this way sort of now sort of has a different kind of maybe psychological value or something to us, because it's saying, what this is really saying is that this particular cubic polynomial, this particular cubic function, can be expressed as the product of this quadratic function, this linear function, plus this like kind of constant term. All right, and we have words for all these things. This thing here, this is called the dividend. These have like old kind of like sort of like Latin origins. The dividend is like the thing that you are dividing, and I'll add it up here too. Dividend. What is the name for the thing that you get when you're done dividing? Yeah, this thing here is called the quotient. The quotient is just what happens after, it's the result basically of dividing. So here we have sort of a quotient. And does anyone know the name? Oh yeah, that was probably the hardest one. This one is kind of famous. What's the thing that you divided by? Yeah, the thing that you divided by is called the divisor. So this is the divisor. And then, of course, the thing that you're left with at the end is the remainder. So here we have a remainder. Okay. And so, what we have now is like a sort of a more, this particular polynomial is an example of a more general phenomenon, which is that any polynomial can be, if you take any polynomial as the dividend, it can be expressed as the product of a quotient, a divisor, plus some kind of remainder. So a dividend, a function, a polynomial can be represented as a product of a quotient and a divisor. All right.
I have a question.
Yeah.
I thought the remainder was a constant.
So the remainder is a constant in this case, but the remainder is not necessarily always a constant. For example, you could end up with some kind of remainder, like if you divide, oh boy, x, well, just to take a really dumb case, x cubed plus 1, no, that's a bad case, x cubed plus x, and you divide by x squared, then what do you end up with? No, yeah. Oh man, x cubed plus x plus 1, there we go. Yeah, good, okay. Without even doing this, just like what are you going to end up with? You're going to end up with x plus, and then you'll just have x plus 1 over x squared. Right? And you can't divide any further because, you guys cool with this question and my answer? Okay, so actually that's kind of like a good hint to the sort of thing I wanted to talk about now, because these polynomials all have degrees, like this has degree 3. It's like the degree of the highest power, this is a cubic, quadratic, etc. So what can I say? There's several observations I can make about the degrees of these various polynomials and their relationship to each other. Anyone want to say one? You're calling some people? Call them. Or should I not call them people because it's like we're videotaping? I don't know, whatever. Who wants to volunteer? Let's do it that way. Yeah.
They like go down.
They go down. Okay, and you a little more specific than that.
Like the highest magnitude or degree is like x, and then.
Okay, sure. Although I don't think any of that. I don't think that's necessary. Yeah, Valentina.
So like kind of the divisor has to have a lower degree than the dividend, because otherwise you're just like dividing with like scalars instead of like.
Okay. Sure. Yeah, you probably can't divide by. Well, I think actually maybe you can, right? Because you can do.
Well, I guess you can.
You
but
can
it's,
do like
stupid.
x squared over x cubed plus 1. She says that's stupid. Maybe she's right.
Doesn't everything just end up in the remainder? So it's just like x squared over x cubed plus 1 equals x squared over x cubed plus 1.
Sure.
Because the quotient.
Yeah, okay, so maybe I like that. Okay, more other things. Yeah, sure. Yeah, I think that one, he's like, look, when you do the division, it's always the case that these two, when you multiply them back together, like give you this basically, like give or take like some extra stuff. So I think that the degree of f has to equal the degree of q plus the degree of the divisor. I think that's like true, yeah? Yeah.
The degree of the remainder is always 1 less than the degree of the divisor.
Yeah, I don't think it actually has to be 1 less, but it definitely has to be less. Yeah, this is the sort of a key observation as well, that the degree of the remainder must be strictly less than the degree of the divisor. Which I'm calling D. Yeah, so he's just noting, right, that like you're always going to end up in a situation where the degree of the remainder is less than the degree of the thing you're dividing by, because if it weren't less, then you just keep doing your division, right? The very division algorithm itself says keep going until you can't go anymore, and if it were equal to or greater than, you just would keep going. Okay, good. Yeah, I think that's good. All right. Blah 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 blah. Good. All right. So, both, can you move the camera to like somewhere else? Like maybe more like go back to it. All right. So, for every single thing that's about to happen on this board now, for everything that's about to happen on this board, we are going to focus on the special case where the divisor is of the form x minus a. And so often do we divide polynomials by x minus a that we are going to, everything that we're going to do from now on is going to only focus on that particular phenomenon. Okay, so first let's do a polynomial long division problem. So here we go. X all over. Okay, go. I got that. Is that what you got?
Yeah.
Okay, cool. Alright, polynomial long division. I am an expert. So the answer to this problem is 6x squared plus 3x minus 1 and then minus 10 over x minus 1. Okay, so like great or whatever. But here's the thing. While doing this, did you feel like an overpowering sense that like almost all of the numbers you're writing down are like not worth writing down? For example, we can make this sort of like with Gaussian elimination and when we invoked matrices for the first time. We could probably do this like way more efficiently because, well, for starters, the algorithm only works if you leave like an appropriate space for every like degree of the polynomial anyway. So you could imagine all of the x's just like disappearing off the page. Would you still be able to tell exactly what's going on?
Yeah.
I claim yes, right? Because I know that the one all the way on the right is the constant. I know the next one is linear, quadratic, etc., right? Okay, so that's one what sense in which this is like kind of inefficient or something. And then the other sense in which it's inefficient is as I'm agreeing in advance that I'm only dividing by things of the form x minus a, then like this coefficient is always 1, right? So like I kind of know exactly how many times this is going to go into 6x cubed. It's going to be like 6 times, right? And then, and like again, how many times does x minus 4 go into 3x squared? Of course it goes in 3 times, right? So I'm sort of like wasting my time like writing the same number over and over again. Okay, and then also, I sort of don't need to waste time like this is kind of like a check move, right? Where you like take the 6x squared and you multiply it back through. But of course you're always going to get 6x cubed, right? Because like you set it up that way. So that's also kind of just like a waste. All right, I now introduce a new method called ghost polynomial long division. Official term. One of the many reasons why I've been kicked off Wikipedia is because I keep creating a ghost polynomial long division page. All right, ghost polynomial long division works like this. You just ghost away all the x's, and also you like don't write everything down because you like don't really need to. Okay, let's do it. Watch. La 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 la. Okay, so now. Okay, I'm going to write minus 4 here, but I'm not going to write the x because I don't have, what's up? Same problem.
X minus a, so wouldn't you just write 4?
Yeah, or I could just write yeah, that's that's a different kind of ghost. So here I'm just going to write, there's no x, so just imagine there's like a ghost here. All right? That's like where the x would have been, but it's not there because we don't need to write it. All right, and now, what's the original problem? The original problem is 6. I don't need to know how many. Minus 21, I don't need to know how many. Minus 13, I don't need to know how many. And then just like minus 6. Okay, cool? Okay, and now, so what's the very first thing we do? The very first thing we do is you divide x minus 4 into 6. All right, so what's the answer? 6. Okay, so the first step of ghost polynomial long division is to just move this coefficient just right up here, because that's always what happens, right? Because x minus 4 is always going to go into 6 some x's 6 times. Get it?
Yeah.
Okay, and now I also don't need to just like rewrite 6 times x because I know it's going to match up exactly. So I can just go straight for the negative 24. Cool? Otherwise, it's basically the exact same thing, right? Because I know I don't need to bother writing this because those numbers are always going to match, right? Okay, and then I just subtract. When I subtract, what do we get? 3. And based on my understanding of the polynomial long division algorithm, how many times is x minus 4 going to go into 3? It's going to have to go in 3 times, right? So again, the thing I get from subtracting just gets immediately sent up there to be the next coefficient in my quotient. Okay, and then, so I sort of have like 3 then times x minus 4. Again, wait, what am I doing now? Oh yeah, then I'm supposed to like bring down this negative 13, I guess, right? So, yeah, I forgot my own goofy plan. Yeah, okay, good. So then, yeah, oh yeah. So I had to bring down the 13. Okay, and then 3 times x is going to just be that, but I don't need to bother writing that. So instead I just do 3 times negative 4, so that's like negative 12, yeah?
Yeah.
Okay, and then I can just subtract that. What do I get? Yeah, I get just like -1. And then finally I bring down the -6.
Yeah.
What's up?
One
We gotta bring the
doesn't
one.
Oh, I forgot to put the 1 up. Yep. Good. Yeah, then this -1 just gets sent up here. So that's like -1. Also, I guess there's like some things here. Yeah, good. All right, and then the final step is to do -1 times, I don't bother writing it, and then I just get 4, and then -6 minus 4 is -10, and then the algorithm just stops. All right, cool? All right, yo, wait, hold on, wait.
Can you like not bring down the
Yeah, you could even probably not bring down the -13. Yeah, we can talk about this in the talk page of the Wikipedia page for Ghost Polynomial Long Division. Possible improvements. Okay, does everyone see how, at least in theory, this is more efficient? Because you're just like writing fewer characters. It's probably not as efficient because it's like annoying and confusing. But it's at least, perhaps, it's an advantage. Okay, well, Sude wants to say something, but I'm not going to let him. I think what he wants to probably say is, yo, I think I can make this even more efficient. Because after all, someone was just complaining a second ago about how this -13 is like repetitive and some stuff like that. And so actually this whole thing seemingly could just be like collapsed into like a tight little box. Aha!
Oh, wow.
No, not amazing. Well, I guess, kind of. I guess anything can be amazing. Okay, so I now introduce to you this thing called synthetic division. And this might be something that you like learned before or something, but maybe not. What is synthetic division? It is a more efficient form of ghost polynomial long division, which is itself a more efficient form of polynomial long division. It only works in this special case when you're dividing through by x minus a. Okay, here's how synthetic division works. Ready?
Yeah.
It goes like this. It says, okay, first of all, apparently from ghost polynomial long division, the only thing that's actually relevant are the coefficients. So let's just start with just writing out the coefficients. So 6, -21, -13, and -1. Okay, cool.
It's -6.
Did I just, what am I doing? 6. I'm just
Yeah,
like,
the last one's -6.
yeah, good. Sorry. Whew, tough crowd. Okay, 6, -21, -13, -6. Good. All right, and now I am dividing through by x minus 4, yeah?
Yeah.
Okay, but instead of writing x minus 4 or blank minus 4, I'm just going to write 4. Okay? And now, watch this. Going through these steps carefully, let's look at what's the very first thing you do in ghost polynomial long division? No, the very first step.
Oh, the 6.
In ghost.